circuits and controllers. All right, let's go to section 430.1, the scope of Article 430. Article 430 covers motors, motor branch circuits, feeders, the protection, overload, control circuits, controllers, motor control centers. This is a big deal. And in my textbook, there's two ways that I think you can become an expert in motors. Number one is take a look at Article 430, get your code book out, highlight it, tab it, and mark it. And of course, we're going to cover a little bit of information today. Also, we have a separate course on electrical calculations, and there's a specific DVD on motor calculations that we get a little bit more in detail inside as far as calculations. All right, let's go on. 430.6, the full load current versus the motor nameplate current rating. Full load current. When the code uses the term full load current, it's referring to the actual National Electric Code values. And that's the values that's listed in tables 430.248 for single phase and tables 430.250 for three phase. So I really suggest that you take the time, you stop it, you look at table 430, 248, because they moved it around, and table 430, 250, single phase and three phase. Now, Ryan, there's a lot of tables in there. And so what I did, matter of fact, let's take a look at what I did back 30 years ago when I was in 430. I have a tab on 430, 440. Here's my tab on motors. I'll put this up here, Scotty, so you can see it. Start in the beginning here. I marked DC, so I wouldn't screw up. Over here, I marked it single phase. I even put formulas on how to calculate the VA of a motor. I circled the heading. It said full load current. I wrote FLC. I even made a cross-reference. Look back here in the code book here. On the top here in the code book, I made a cross-reference between this handbook and the National Electric Code. So if I wanted to go to the code book and not have a handbook, I'd be able to make a cross-reference. That's the kind of detail I had. Let's go to the next page here. Then I had three-phase. I identified three-phase. I made the note FLC. I circled the word induction type because it's easy to go into a table and not realize there's multiple things in there. And synchronous type. I made how to calculate the VA of a motor. So when I wanted to do calculations later on, I didn't have to figure out what was going on. And when I went to my code book, let's take a look at 430. Let's see if I did 430.6. What did I do on 430.6? Quickly turn there. 430.6. Nope, I didn't cover it at that time. But you can see my notes in here. I even put little pieces of paper, had something in there, highlighted things I thought were important in pink, circled words, made references to other code rules. In red, I even identified what step number, if I was doing a calculation, that would be step number 3. Okay? This is what you have to do. You know, nobody told me to do this. I mean, I'm not a smart guy, so I don't remember things very well. So by me putting things down, and when I get to it again, I'm like, oh yeah, I remember how that works out. So the code book gives us the full load currents. So you have the code book currents, and what you also have, is what the motor nameplate rating. Let's take a look at the graphic again. So you have the motor nameplate, and then you have the code book full load currents. You use the table of the code to size the conductors, the disconnects, the short circuit and ground fault protection devices, and then you use the nameplates to size the overload protection. And right now you're like, I don't know what you're talking about. Okay, and nothing else, you should know this. There are full load currents listed in the code book, and there are nameplate values that's listed on the nameplate. And we got to be careful in which one you use. Just like you don't use a three-phase table for a single-phase motor full load current, just like you don't use synchronous motors for induction motors. In other words, you got to be careful in what you're doing. So do what you need to do to get rid of tables, cross them all out. You don't have to do what I did, but at least you can get rid of things that definitely don't apply, or circle things and highlight things that you do apply. I really believe, electrician in the field, should have the ability to size the wire to a motor. I really don't think we're asking too much. You should be able to go out there and say, hey, got a 5 horsepower motor, 208 volt, 3-phase. Boom, let's go out there, size the wire, size the protection. You know how to size the raceways and the conductor size. Why not? I mean, aren't you like an electrician? You know, aren't you an engineer? Shouldn't you be able to do this kind of stuff? All right, let's take a look at the rule. Motor full load current rating. Now, full load current rating is FLA. That's not full load current. Ryan?
Well, I was just going to mention while you're on that previous graphic, especially if you're new to motors, that's something you need to burn right into your frontal lobe, is what is FLA, what is FLC, and what do you use them for? You'll never get any question right on a test if you don't understand this.
FLC, right? The code book.
Right.
FLA is the nameplate.
Yes.
Full load amps versus full load current. Full load amps, well, there'd be no reason for you to calculate this unless you had an exam question saying, hey, I have a 1.5 horsepower motor, and it's 3-phase, and it gives you the efficiency and the power factor. Well, then you take the formula, 746 times horsepower divided by volts divided by the square root of 3 divided by efficiency divided by power factor. And of course, there was no reason for any electrician to have to do this. Okay, there's no reason. You're going to nameplate. But a manufacturer had to calculate out the full load amp somehow. They need to know what horsepower is it, what's the voltage, what's the efficiency, what's the power factor, single phase, 3-phase, and they kind of go through the calculations, and that's how the nameplate is calculated. But guess what? We don't care. We don't use nameplate. So who cares? We're never going to use a nameplate. Let's go to 430.22, conductor sizing. Conductors for a single motor are sized no less than 125% of the table full load current, not the motor nameplate current rating. We get the table full load current, 247 for DC. I don't think we see a lot of DC motors. Maybe there's a space there in that comma. 430.248 for single phase, 432.50 for 3-phase. You use the code book, not the nameplate, to size the conductor. So let's get an example here. If the motor is 7.5 horsepower, and this is going to be 3-phase, then 3-phase, I would go to table 430.250, and that says that the full load current is 22 in the code book. Well, I sized the conductor no less than 125% of that. 22 times 1.25 is 27.5 amperes. And then if I remember right, it was 110.14 C1. Ryan, double check me. I don't know if it's C1B that says that motors for under 100 amperes, is it C1B?
C1A4.
Oh, C? Oh, yeah, A. Like I say, C1, because it's 60 degrees C is A. C1A4 in motors, that motors are sized to 75 degrees C. So if the motors are 75 degrees C equipment and the breaker is 75 degrees C, well, then I would just go to table 310, 15B16, go to the 75 degrees C column. When I'm talking about all this, put me on pause. Get your code book. This is not something, when we get into calculations, this is not something you should be sitting there. And actually, I don't have a problem with that. I don't have a problem you watching me go through just to kind of see what I'm doing, put it on pause, go back and watch it again, and then pause me as you go along as I step you through each of the functions. Go to this code book, do this number, good. And I give you these references. I mean, I'm throwing out these references not because I'm trying to impress you. I'm throwing out these references because I want you to say, oh, let me go check that. You should be looking at, every time I give you a code reference in this DVD, if it were Mike Holt, which I never had anything like this here, and this is why I produced what I produced, because I was so frustrated. If it were Mike Holt and I had this DVD, I'm going to tell you one thing. Every single time that guy used a code reference, every time, if he said 110.14C, and guess what I would have done? I would have found the guy made so many mistakes when he made references to the code because he said 110.14C1C, or it really was C1A4. So I would have caught those little tiny things because the guy's trying to say it real quick and he makes slightly off and maybe even use the wrong article. Well, if you take a look at this and you knew he meant to say this. So I'm catching all these little things and I'm going to the code book back and forth. And guess what you're going to find out? Wow, how often do you use this rule? How often do you use that rule? How often does this come up? How many times you're going to be able to become an expert in the material. So don't just listen and move on. Listen, go back to the DVD, back and forth, back and forth. So back to our calculations. 22 times 1.25, 27.5. I go to table 31015B16. I go to 75 degrees C. I look it up. I need a wire rated 27.5 amps, and I guess it's 10 gauge. It's just that simple. Even though I say it's just that simple, it's the simple things that really catch you. It's like, Mike, where in the code does it say this rule? And I'm like, gosh, it's such a simple rule that everybody knows it that we never look it up. Those are the hard ones. Those are the easy ones to trip up. Watch this. We size the conductor to the FLC, okay, which is in the code book. Let me tell you what you don't do. If you're physically on a job site and the motor is there, you do not ever look at the nameplate as it relates to conductor sizing. You don't look at the nameplate because that's not what the purpose of the nameplate. And let me tell you why we don't look at the nameplate. Because the code book gives you a value of currents. The motor that you put in specifically might not be the motor that you're going to replace someday, because we don't know the efficiency and the power factor of every motor every single time. So when the code says, take a look at the graphic here, this motor draws 22 amps full, this motor has an FLC of 22 amps, I'm sure that most 7.5 horsepower motors, 230 volts, three-phase, are not 22 amps. But there probably is a motor, depending upon the NEMA configurations, that it could go up to a maximum of 22. So we want to make sure we have a conductor there that will always be available for a 7.5 horsepower motor, not for the motor that you specifically put in. So we do not size conductors based upon the nameplate. We have to make sure we use the full load current. Let's go on now, sizing conductors if you have several motors. Conductors must be sized not less than 125% of the largest FLC plus the sum of the FLCs of the other motors. So if I have two 7.5 horsepower motors, I do not look at the nameplate. I look at the code book. We already determined it was 22. So 22 times 1.25 plus 22 amps comes out to be 49.5. We're going to go through that mental routine that we're going to use 75 degrees C terminals because the breakers are rated 75 degrees C. Going to table 31015B16, I need a wire rated 49.5 amps. 8 gauge wire is rated 50 amperes at 75 degrees C. Pretty straightforward, not complicated. Don't go to the nameplate rating. All right, let's move on now to the protection of a branch circuit. 43051, branch circuit protection, the general requirements. A branch circuit, short circuit, and ground fault overcurrent device protects the motor, motor control apparatuses, the conductors against short circuits or ground faults, but not against overload. We talked about this when we were in Article 240. We talked about the definition of overcurrent. We talked what an overload was, what a short circuit was, what a ground fault was. And generally, when you provide overcurrent protection, overcurrent, then the definition of overcurrent, Article 100, has to do with overloads and short circuits and ground fault. Generally, when you provide overcurrent protection, you put in one device. It's a fuse or it's a circuit breaker, and it protects against overcurrent, short circuit, ground fault, and overload. When you get to motors, we have different characteristics. This is not a light bulb. This is not a computer. This is a load that when you first turn on, it has a unique set of properties, and then it ends up changing once it gets to a certain point. So you have to be able to consider the different. This thing is moving around. It starts here and it goes there. So we got to be able to size it for here and then there at the same time. So we're going to take a look at the rules here. We need to provide overcurrent protection. Watch this. This is an overload. That's going to protect the motor against excessive current. And then over here, we're going to have a fuse breaker, and this breaker is going to protect this motor against short circuit. Right now, this motor has a full load current rating, full load, that's a nameplate. It has a nameplate rating, we probably should indicate, of 16 amps, the nameplate. But if it was drawing 24 amps, well, then we have a problem because it's overloaded. So what's going to happen? These overload devices, okay, they are designed for slow current rise, probably slow temperature rise, probably more than slow current rise. It's a slow, it would be a slow temperature rise, and it's a current that's going to be long duration. and the device responds slowly. So if I put 24 amps on a 16 amp overload, this baby is not like instantaneously opening. What it does is it works off of heat. So if you put 24 amps on a 16 amp intended load and you provide an overload device that's looking to protect that motor of 16 amps full load amps, well, if you put 24 amps on there for just a second or two or a minute or two and it comes off, it's like, oh, okay, we're not worried about it. But if it's going to be on there for an extended period of time, now the overload device is going to be thermal. It's going to sense it. Of course, it can be done electronically as well. And then once it gets past the point of realize, okay, wait a minute, now this overload, this current has been lasting too long. And we're not talking about seconds. We're probably talking maybe in minutes, depending upon what the overload is going to be. So it's slow responding. Now let's talk about short circuit protection. What happens if it's a ground fault or a short circuit and it draws 1200 amperes? Well, these overload devices are not going to respond because they take a long time to pick up heat. However, the short circuit protection device up here is intended to pick up a short circuit. So your short circuit and ground fault protection devices are designed to protect against short circuits. The overloads are designed to protect under an overload condition. And when you have the short circuit ground fault protection and the overload, then that provides overcurrent protection. Short circuit and ground fault devices, I'm making a statement now, are sized between 150 and 300% in accordance with 430.52 table. Short circuit and ground protection is designed for fast current rise, short duration, and a fast response time. Let's go a little further. We can see what we're talking about. Here we go. You have a motor that's starting, and it starts at lock rotor current. You see, you take a winding of a motor, and you wrap it inside the motor, and then you turn it on. Well, the instant you turn it on, it's a dead short. But as it starts carrying current, alternating current, it has an expanding, collapsing magnetic field. And we covered this in the electrical theory class. Very, very important that you get my electrical theory course and you go through that whole thing because it's practical electrical theory. I'm just going to hit a couple points here and not explain how this works out. You have a coil. You have counter EMF. You have magnetic fields inducing a voltage that's going to be at 180 degrees out of phase of the applied voltage. And what this is called, this is Lenz's law. This is where Lenz's law, it starts short circuit, the inductive reactance gets involved, and all of a sudden now it changes the impedance of the circuit. You should be understanding everything I'm talking about. If not, you need the electrical theory library and go through that. It changes the impedance of the circuit from this low impedance, because we had only resistance, you're now adding reactance, and the reactance and the resistance combine together, which increases the impedance, and it changes the current from starting current to running current. Simple version here. Generally, motor starts at lock rotor current. Lock rotor current is approximately how many times running current? Some of you guys maybe already know this. The answer is 6. It all depends on the design of the motor. Very, very high efficiency motors will have a very high inrush current. Now, I'm going to get a little bit off schedule here, or just a little bit off topic. High efficiency air conditioners, scroll cage air conditioners, high efficiency. One of the disadvantages to them is that when they start at short circuit, and the reactance is so low that that short circuit current stays high for enough time that all of a sudden the lights in the house, they just do a little tiny dim, and then they rise back up again. We're only talking about a couple cycles, but the eyes will notice a slight, like 1% change in illumination is going to be the square of that. When I say 2%, it's going to be 4% change, and the eyes can sense that. So air conditioning loads that are high efficiency have low inductive reactance, because that's how you get efficiency out of that, and it causes the current to be high. So fault current would be much higher if you had a fault condition. Back over here in motors. Motor starts at lock rotor current. The higher the efficiency, the higher the lock rotor current. So it starts lock rotor current, and then it starts going down, and then we have what? We start in picking up reactance. We start getting, the impedance goes up, and then all of a sudden now we're running at this. Let's say this motor is drawing 22 amps. Well, that's what it's drawing. But it might have started at what? 22 times 6? I don't know what that comes out to be, 132 or something like that. So guess what? During the starting current, I need to provide some protection. Well, I can't provide overload protection because this is too fast. So I have to provide short circuit protection that if during this period of time there was a short circuit. Let's say the short circuit was 10 times. See, short circuits are considered to be about 10 times the rating of the protection device. So 10 times. So if you had 22 amps, it's going to be about like around 200 amperes, something like that. Well, if you put 200 amperes on a breaker, well, it didn't expect to be that high, so therefore it's going to react in that particular case. So it starts at 6 times. Let's size the protection device, allow that motor to start at lock rotor current. So there's a formula in the code, and the code says, well, use this percentages. And it also says, well, if you use this percentage and you put that breaker in there and it doesn't hold, like, okay, put a bigger breaker. It doesn't hold. Okay, put it. In other words, you got to put a breaker to allow it to start. But here's the disadvantage. The larger the rating of the breaker that you go to start, then you obviously have no overload protection. You can't protect that motor that draws, let's say, 22 amperes if you're going to be starting it at a protection device at a certain percentage significantly above the rating of that motor. So look at the rule here. Short circuit protection is going to be sized between 150 and 300%, right here. Overload protection is between 115 and 125%. So you can see we can protect the motor when it runs, but we need to start the motor and get the short circuit protection. 43052, branch circuit, short circuit, and ground fault protection. All motors, a motor branch circuit, short circuit, and ground fault protection device. Now, they didn't say motor overcurrent device. They said motor branch circuit, short circuit, and ground fault protection device must be capable of carrying the starting current of the motor. That's what the code says. It has to be able to allow it to start. And then there's a table. And basically, the table says, depending upon the type of the motor, depending upon the type of the protection device, you have a different percentage. If you're going to be using other motors, not wound rotor, let's say not DC, let's just say we go to other motors. If you're going to use a one-time fuse, then the fuse would be 300%. If it's a dual element fuse, then you go 175. And if it's an inverse time breaker, then you're going to go 250%. For the convenience of this presentation, let's just assume that we're going to be using circuit breakers. And if I'm using circuit breakers, I'm going to use 250. If I'm using fuses, then it'll be identified in the example that we have, if we have any fuses. So let's go into the example now. Let's take a motor, 2 horsepower. It has an FLA, full load amps, which is the nameplate of 11 amps. But it has the code book, so we need to say in their nameplate, and then 12 amperes, which is the NEC. Well, we size the conductor based upon the FLC, which is the listed in the code book. 12 times 1.25 is 15 amperes. No problem there. 15 amps, you go to 310-15B16. We're going to go to 75 degrees C because it's motors, assuming everything is rated 75 degrees C. 14 gauge wire, rated 20 amperes, and that's how I'd size the conductor. Not anything more complicated than that. Take 125% of the full load current, size your conductor. Now look what happens here though. See, we're in 43052, C1. We're talking about protection, but we're talking about short circuit and ground fault protection. We're not talking about overcurrent protection. That table tells us that inverse time breakers that go 250%. 12 times 2.5 comes out to be an even 30 amperes. You go to 240.6, standard size breakers. It's a 30 ampere breaker. So you put 30 ampere breaker on 14 gauge wire. And the purpose of this breaker is to protect the 14 gauge wire, to protect the controller, to protect the motor circuit conductors and the motor under the condition of short circuit and ground fault. It's not to protect the motor and the conductors and the components against overload. Overload would require you to have an overload protection device. Now, some people struggle with this, with the fact that, wait a minute, you're telling me I can put a 30 amp breaker on a 14 amp wire? Well, I'm telling you, you size the wire to the code, and the code says you take the full load current at 125%, then you go to the table 310-15B16, and you go to 75 degrees C column, and you size the wire, and you're done. Has nothing to do with the protection. And I'm saying, how do you size the protection? Well, you go to 430.52C1. You go to the table. It says inverse time breakers, 250%. You go to the full load current listed in the code book. You get the full load current times 2.5. You look up that device. You go to 240.6. If it doesn't correspond to the standard size on the protection device, you go up to the standard size protection device, and we're done. But Mike, a 30 amp breaker, 14, listen, if you take 14 gauge wire and you put it on a 30 amp breaker and you have a short circuit, or you have a ground fault, that current is going to draw more than 30 amps under short circuit in ground fault condition. Not overload. We're not trying to protect against overload. That's why it's called the short circuit ground fault protection device. It will protect the wire against short circuit and ground fault. Now, you might not like this. Oh, I don't like this. Okay, fine. I don't care. But if you're going to take a test, how about if you know how to do it right? You know, you make sure that you know how to answer the question and get the correct answer on that. And that's how it works. Let's go on to the next graphic. Okay, let's take a look at an example about 43052 C1 exception. We have a 7.5 horsepower motor, 230 volts, three phase. We go to 430-250. We find out the motor draws 22 amperes. Okay. We size the conductor to 125%. So we're going to take, okay, we don't have an example there, but let me just do the number. Oh, we did it previously. That was 22 times 1.25 came out, I'm going to, whatever the number was. It was a 10 gauge wire, but we're talking about the exception here.
27.
The protection. You size the protection 43052C table. The general gives us 250%. 22 times 250 comes out to be 55 amperes. 240.6 does not list a 55 ampere protection. This exception says that when you do the calculation on the branch circuit, if it doesn't correspond, go up to the next standard size. So we'd have a 60 amp breaker with 10 gauge wire. Again, this is short circuit and ground fault protection, not overload protection. Let's just do a little summary here. 43052, and the table 43052 tells us that we size the short circuit protection at between 150 and 300% depending upon the motor type. You size the conductors to the motor on 43022A. You size the conductors at 125%. And the overloads are sized between 115 and 125%. So if you have your short circuit protection and your overload protection, that will provide the overcurrent protection required for the circuit. Now watch this. More than likely your breakers are going to be 250%, your conductors 125, so you can expect that your protection is going to be greater than the conductor by a considerable amount. This is a different example. 28 amp full load current for a 5 horsepower 230 volt motor. We ignore the full load current for the purposes of sizing the conductor. We take the conductor, 28 amp full load current at 125%, comes out to be 35 amperes. We go to 75 degree C column, table 31015B16. I guess that comes out to be a 10 gauge wire. We don't need to have the insulation on here, 10 American wire gauge. And so we use the full load current to size that. You size the protection at 250% of the full load current, which was identified on the table. We do not use the nameplate. 28 times 2.5. This comes out to be exactly 70 amperes. And therefore, we're going to size this protection at 70 amperes. So we use the full load current for sizing of the conductor and the protection, and we use the motor full load amps for sizing of the overloads.
So kind of a interesting point. We didn't cover overloads. How you size them, you know, how do you...
There's a reason why I did not put any slides on sizing of the overloads, because we don't do calculations in sizing overloads. If you're taking a test, you do. The way you size overloads is you get the overload protection device, and you look at your motor nameplate rating, you take the cover, you look at it inside there, and it gives you current ratings. And it says, okay, what is your current rating? And when you figure out what your current rating is, in this case here, the current rating is 26. You look at 26, you take the cover. We don't do calculations. And then you find the cover, and then you have dip switches, and you change your dip switch settings, or you go out and you buy an overload device, a mechanical device that you're going to put, an electromechanical device, and you put it in there. The code does provide all kinds of percentages inside here. If you were actually going to do the calculation and you were actually going to put an overload device, that would only happen if you were going to be putting in a fuse. Other than that, the overload device is part of the controller, and that's the reason why I didn't get into the calculation. If I'm in an exam prep class, well, yeah, you're going to take a test. They're going to ask you a question. Hey, I got a motor with this service factor. I got this temperature rise. I got the nameplate rating. I get the FLC. What would be the overload device size? Then we're going to get into all the calculations. Do you follow what I'm saying, Ryan? And that's the reason why I didn't want to cover it here, because it doesn't belong in understanding the NEC if I have to compromise time. That is more of an exam preparation and why and how you do that. And I'll tell you a short little thing about that. It is important to understand overload protection. Short version story, was living in Fort Lauderdale. I had a boat lift, and every once in a while, I noticed that when I was barefoot water skiing, I come back, my boat lift was up. Well, when I got back, my boat motor lift was up while I was skiing. I didn't understand what happened, and my motor burnt out. So I go out and I buy a $400 replacement motor, stick it back in there again. 6 months, a year or two later, my lift is up. And I'm not a smart guy, but I'm starting to pick up a trend here that when my lift is up, my motor's burnt out. Guess what? My motor's burnt out a second time. All of a sudden, everything is fine. I can't figure out what it is. About a year or two later, I come back and I see my lift up. That means it's the third motor that burnt out. What I found out was this, and I happened to see this. There was a bird that landed on the handle of the lift. See, this takes the lift down, this takes the lift up. A bird came over to the handle. When he landed on the handle went down. So when he went down, he did what? He pushed off to fly away, and the handle went into position that lifted the motor all the way up. I had no overload protection on this half horsepower motor because it ran back over to the source. Now, what I did was I added a fusible disconnect. I look at the motor nameplate. It drew 6 amps. I sized an overload device. I couldn't find one at 115, 125%. I didn't know what to do. So I went ahead and I bought a 6 amp fuse, put it in the fusible disconnect, and I never lost the motor again. So if you're really trying to protect the motor against overload, you need to have overload protection. Now, many times overload protection is internally part of the motor, but many times you can get small motors that do not have internal overload protection. And if you want to protect the motor against overload, you need to understand 430.31 and 32 in sizing overload devices. So that's why I didn't want to get too detailed, other than I want to give you a conception of overloads, but not all the calculations involved. Eric, do you want to make a comment before we're done here in 430?
Yeah, everything you're saying in overloads is correct. There is one caveat. When you're dealing with electronic overloads that have potentiometers, and these things have scales on them, and some of the manufacturers, specifically ABB and Cutler Hammer, will say, look at the nameplate, and if it says 12, just dial the potentiometer to 12. But if you have a Siemens overloads trip at the setting. So you do actually have to make the calculations on those.
All right, excellent. So make sure you look at our book. We have examples, and if you really want to know more about that, we'll get into the calculations portion that we'll be recording in another course. Let's go on to 430.62, feeder protection. Boy, this is a rule that I think nobody ever gets. I mean, I teach this for years. Feeder conductor overcurrent device size, not, you know what I'm going to do? I'm going to underline this thing while we're all looking together here. Maybe that'll help you. Size not greater than, okay? Not greater than. So whatever this answer is, it's not going to be greater than whatever our answer is going to be. Then the largest rating of the branch circuit, short circuit, and ground fault protection device, so the largest protection device of the motors, plus the sum of the full occurrence of the other motors in the group. Let's go with an example here. So this device cannot be greater than whatever the calculation is going to be. And unfortunately, the calculation is perfect here. So we know we have a 5 horsepower motor, and it's a 70 amp breaker. And the reason we have a 70 amp breaker, I don't know if we did a calculation previously in the book. 70 came out to be 28. Get your calculators out, guys, if you would, for me. What's 28 times 2.5? Does that come out exactly 7? I think it comes out exactly 70 amps.
70 exactly.
That's what we did. All right, so that's a 70 amp branch circuit, short circuit protection. How about a 3 horsepower motor that draws 17 amps? So 17 times 2.5 is
42.5.
What is it?
42.5.
And it doesn't correspond to standard size, right?
Right.
So therefore, branch circuits can go up to the next standard size. I got a 45 amp branch circuit protection. I have a 70 amp feeder protection. The feeder protection device is sized no less than the largest branch circuit protection, 70 amps. You can see how Mike highlighted this in red, plus the full load current of the other motor. Not greater. We have it in there. Where's it? We have the word in here, not greater than anywhere? Yeah, I don't know where it's. Okay. So it's not greater than 70 plus 17, then it would be the next size down. So not greater than 70 plus 17, not greater than 87. Well, you can't put a 90 because obviously that's greater than 87, so you have no choice but to put an 80 amp device here. Okay? And that's how now, just so you have an idea what is, I'm not even going to go any further. Let me just stop it right now. This is not a calculations class. I could go on and get a lot more deep, though. So I'm going to stop there. By the way, the circuit conductors on this was sized at 28 times 1.25 plus the 17, so 25, that's 35, that's 45, that's 52, I think. So I needed 52 amp wire at 75 degrees C with 6-gauge wire. So you have a 6-gauge wire at 80 amp breaker. People go crazy. Well, oh, no, this is how you do motors. Ryan?
Well, why don't you verbalize how you did that there?
Okay. Good point. I take the 28 amps. I said it, but I said it so fast. I take the feeder conductor on 430/24. I take the 28 amps times 125%, which is 35.
So the biggest motor? Is that,
Well, I take the largest FLC.
okay.
Okay, take the largest FLC at 125%. That's 35. The 28 times 1.25, 35 plus 17, 35 plus 17. Oh, no, that's 45. That's 52, right? And so I need to have a 52 amp wire here and 75 degrees C, table 310, 15B16, and I guess that'd be 6-gauge wire on an 80 amp breaker. Thank you very much for slowing me down and having me repeat that.
Hey, Mike.
Yes.
I just really want to, I know you said this, but I really want to point out that when you do size the feeder protection, you're sizing it on the actual device, the largest actual device. So that's a 70 amp circuit protection on the largest device.
Yes, you saw that. Oh, I understand what you're leading
Yeah,
up
it
to.
has
I don't
to
want
be
to
the
go there
right.
because if they're tilting their head like a little puppy, wondering, I wonder what that means. And I'm not even going to go there. But there are some people that think something else. So you base it on the 70 amp breaker plus the FLC,
Right.
and I'll go there. There's a possibility that if I'd used a different current over here, that this could have come out to be, let's say, 68 amps. Well, if it's 68 amps for the branch circuit protection, you'd have put what? A 70 amp protection. But some people would have thought that you take the 68 amps plus the 17.
Right.
And I knew that's what you were leading up to,
Right.
Erica.
And
No. It's
very
not your
important.
calculation of the 250% plus the FLC at 100%. It's, well, you do your calculation, then you round up to your breaker, then you use your
Right.
breaker plus your full load current. So
Right.
I knew exactly where
That's
you were
right.
leading into. I was afraid to get in there because I was afraid we had it, but I felt that the guys could handle it, so let's just do that. Good point. 430-102 disconnect requirements, going to go very quickly. You need to have a disconnect for the motor, and you need to have a disconnect for the controller. And the disconnect for the motor must be within sight of the motor, and the disconnect for the controller must be within sight of the controller. Basic rule. You can, and this is your controller, a time clock. You can't have a controller ahead of the disconnect. Well, actually, this problem here is that you got to disconnect within sight of the controller. I'm sorry, within sight of the motor. Here's your controller, and the disconnect is not within sight of the controller. So in a swimming pool, you can't put a time clock before your disconnect because you got to be able to disconnect the controller. By the way, I didn't talk about the definition of a controller. And Ryan, look at that. I think the controller is probably defined in Article 100 because it would think, or is it on 430.2?
Well, you got to be careful because it's in both, but it's in two different contexts.
Oh, really?
There's an Article 100 controller and there's an Article 430 controller.
Well, okay. If the code in 430 uses the term controller and there's a definition of a controller in 430, then I'm not going to 100. You see how subtle this is in the code? You see how you got to really, really be aware? So what does 430.2 say as a controller? 430.
And the first part's important. For the purposes of this article, a controller is any switch or device that is normally used to start and stop a motor by making and breaking the motor circuit current.
Hold on. It's not the push button.
Right.
It's the making and breaking contacts.
Right.
That's the controller.
Yeah.
We're not going to get into that stuff, but I don't want people thinking
Right.
that you have a start-stop button, that is your controller. Okay, your controller is the actual, and we probably should, well, this is a manual controller, so it doesn't really matter here. Okay. All right, let's go on here. Here's your disconnect. It's within sight of the motor. That's your rule. Here's a disconnect within sight of the motor. The controller disconnect, which is within sight of the controller, can serve as a disconnect for the motor if the controller disconnect is within sight of the motor. So you have a disconnect for the motor within sight, a disconnect within sight of the controller, that's fine, or one disconnect can serve as a purpose of the disconnect of the controller as the motor, as long as it's within sight of the motor and the controller. 430.102b exception. You don't need to have a disconnect within sight of the motor if it's impractical. Well, what does it mean by impractical? I believe 430.102b exception has an informational note. And because this rule says, well, if it's impractical, I mean, you can't have a disconnect with the motor. It's not practical. You're like, how could it not be practical? Well, if the motor is in the bottom of a well, obviously your disconnect can't be within sight of the motor. Like, well, you got me on that one. I can see that now. Or if it induces a hazard to persons or property. So the other thing is, if it's not practical or it induces hazards to persons and property, there's an informational note. Ron, do you want to read me the informational note on 430.102b exception that describes, well, what could introduce an additional hazard to persons or property? That's 430. Again, you guys jump on that as I give you that reference. Ron, what does it say about it being the informational note there?
Yeah, it's right at the bottom of the page. They moved it. It says some examples of increased or additional hazards include, but aren't limited to, motors in excess of 100 horsepower, multi-motor equipment, submersible motors, motors associated with adjustable speed drives, and motors located in hazardous locations.
All right, hold 1 second. Read it again to me, and I'm going to parse you as we go along. Okay.
Some examples, motors in excess of 100 horse.
Okay. Eric and Victor, you guys deal with big stuff. And I don't know enough about motors, but apparently if you have a very large motor, you don't like go and just open the switch, right?
Yeah, and I tell you, there's a lot of motors nowadays that are being driven by VFDs, variable frequency drives, and you certainly do not want to have a field disconnect when there's a VFD-driven motor because you'll destroy your VFD.
Does it say that, Ryan, in the
Yeah,
information?
it talks about adjustable speed drives.
Yeah, so you know, if you have a variable frequency drive, you don't put a disconnect in the motor. I don't know enough about that, but apparently when you have the motor running, a variable frequency drive, and then you open the switch, it does something to the equipment, and then all of a sudden you wipe out the electronics of the variable frequency drive. So the code recognizes these possibilities and say, well, yeah, okay, don't put a disconnect with inside a motor. Or in case you have hazard classified locations, maybe it's like, you know, maybe you're better off not having a disconnect there in a classified location. So there'd be other possibility. But for 99% of the applications, a disconnect is going to be required with inside of the motor unless there's some compelling reason, as the code describes, and the information note provides us information and guidance. Let's go to 430. 430.103, operation of the disconnect. Pretty straightforward. The disconnecting means for a motor controller, here's your controller right here, that Ryan read it in 430.2, and the motor itself must open all ungrounded conductors simultaneously and be designed so that it won't close automatically. Well, if you're going to use your time clock, it's possible a time clock could possibly serve as a disconnecting means and could also serve as a controller. There's a possibility. But you might have time clocks that you can't turn it off, and all of a sudden you turn it off, and then you go into work on the motor, and then the time clock goes and turns it back on again. So just be careful. 430.107, readily accessibility. Either the controller disconnect or the motor disconnect required by 430.102 must be readily accessible. So here's an example of a controller disconnect that's readily accessible to the controller. Well, the disconnect from the motor is not readily accessible. And that's okay. One of the two of them have to be readily accessible. Hey, Victor, did you want to say something before we get off of Article 430?
Yes. VFDs, adjustable speed drives, are becoming more and more used in particularly industry and commercial use for energy management and energy reduction purposes. And that creates a problem with sizing the overcurrent protection here, and we've talked about the problems with VFDs with the location of the disconnect. But in order to size the overload, we have to go to Article 430, 130A, and either 1 or 2, depending upon whether the manufacturer gives us instructions on this. 430, 130A1 gives, we size the, just like we normally would size any motor circuit. And if the manufacturer gives us instructions, we go to 430, 130A2, and then we have to follow his instructions on doing that sizing there. And it's generally going to be 125% rather than the 250, because we don't have that large impulse when the motor starts.
Now, what is the rule for sizing the conductors to the VFD?
Well, Mike, the conductor size is going to be given to us in 430, 122 A or B, and it's basically going to be 125% of the value of the VFD.
Excellent. All right, we are done with Article 430.